Black math! Give me some math and I'll give you some flack. Black math!
All right, so 79, let's do 79. We're going to talk about angles exterior to circle. So angles that are exterior to circles.
What lessons are we doing next year? No, not next year.
After spring break?
After spring break.
Well, we're going to end up with, we're going to do 81 and 82 on Thursday. Why? Are you going to be gone?
No.
You just don't want to?
Yeah.
Yeah. But, the following Thursday, we're not going to do anything.
Yeah.
And the following Tuesday as well. So, yeah. So, we're going to do 81 and 82 on Thursday. So, and then I thought it'd be crazy and then do 83 and 84 after we got back from spring break.
Attendance, please.
Took attendance. Okay.
Or you quickly looked down, panicking.
Yeah, I did. I'm good, right? Let me just make sure. Yeah, good.
If you don't mind me asking, how many tests are left of the semester?
2.
2?
That's it. 2. We're just gonna do 2 more tests.
Britlet.
I don't know what that means. Okay, so circles, exterior, angles exterior to a circle. So here's a circle, a nice circle, by the way. Look at that. Thank you. You're welcome.
Actually, it's not symmetrical.
You're not symmetrical.
I know.
Okay, so this is angle 1. And then we've got let's say this is arc B, D here. And then this is CE. Oops. Okay, so here's an angle that's not inscribed, right? Remember, inscribed angle is there, and then we had other angles that were like crossing in the middle. So this is an angle that's outside the circle. So this angle A.
Intensifying the attendance, please. Intensifying the attendance.
Classic binds.
She's really bad at attendance.
I don't hear her name very often. But
Well,
my name's totally gonna be called before the end of the day. So you just wait for it. Then you can laugh.
When we were in her class in 8th and 7th grade, she always forgot to take attendance. Always.
Yeah,
I don't think there was
it's all right.
a day when she did.
It's a lot, but she was newer. She was new. It was a lot to remember. It's okay. So here's the deal. This, when you've got a situation like this, guys, and there's like an angle 1 and 2 there, and then here's arc AB and CD. Do you remember how to find that angle? Measure of angle 1. You guys remember how to do that?
Find angle 1?
Yeah. Which is the same thing as angle 2, right? So how do you find X or measure of angle? Because these are both the same, right? Do you guys remember how to do that? That measure of angle X is just the average of those 2 arcs. So it's AB plus CD divided by 2. So it's like halfway between this measure and this measure, which kind of makes sense. Because if it was right in the middle, then it would be a central angle, which is the same as those arcs. But it kind of makes sense that if you shift it a little bit to the right, then it's going to be closer to that. So it's going to be the average of those 2. Okay? So it's kind of similar to this, but the measure of angle 1 is not half of the sum. It's half of the differences, okay? Because this angle looks really small compared to that. So it's basically measure of arc CE minus measure of arc BD divided by 2. So it's not half the sum like it is on interior angles, but it's half of the difference, okay? So this one's a little harder to remember because this one kind of makes sense. Oh yeah, so you're moving closer to that so that it's going to be smaller than the central angle would have been. So it makes sense that this is the average of the 2 arcs. But this is the half of the difference of the two arcs instead of half of the sum of the two arcs. Okay? So make sure you know that. You have it written somewhere. This is theorem 79.1. Is this formula here, okay? So measure of angle 1, so measure of an exterior angle is equal to the half of the difference of the sum of the arcs that it intersects. So this angle is going to intersect two arcs, this one and this one. So the farther one is going to be bigger, obviously. So subtract these two arcs and divide it by 2. Can you do that? Can you remember that? Okay. All right. So it works the same way when it's like this as well. So if there was like an angle that looked like this, and one of them was like a tangent, it still works the same way. So let's put some letters here. So the measure of angle C is going to be subtract this arc minus this arc, and then divide by 2. So the measure of arc AD minus measure of arc BD divided by 2. Okay? So it works both ways. Even if it doesn't go all the way through, like if one of them is just a tangent, it still works the same way. Okay. So let's just apply it a little bit. If you, let's just do some examples. Just make sure that nobody's waiting and waiting. Okay, so applying. So here's example 2. Here's a circle. Here is a angle. This is 49 degrees. This is 13 degrees, this arc here. So I want to know what angle E is. Well, can you figure that out? See if you can figure that out. You don't really need these letters, but what is the measure of angle E?
8.
So 18 is the guess. So basically measure of angle E is going to be 49 minus 13 divided by 2. 49 minus 13 is 36. Divided by 2 is 18. So measure of angle E is 18 degrees. Pretty simple, right? Can you guys handle that? Okay, let's do another one. Let's find this measure. Here's example 2B. Okay, find the measure of angle D. So raise your hand if you got it. Don't say it out loud. Raise your hand if you got it.
Or both of them tangent.
Yep.
Okay.
Yeah, that top one is supposed to be tangent. So they're both tangent. You got it? You doing it in your head? I love when they don't give you very much information and you just have to figure it out. Because you can fill in a lot of these blanks. And then put it in the formula, theorem 79.1. You got it? All right. Who else? Who's got it? Raise your hand if you got it. Oh, Tristan, are you still working? Okay. I'm gonna wait for you. Tristan, you got an answer?
No.
Anybody else? Are you working tonight or are you?
Yeah, I don't, it's not fitting together.
Right.
I thought it would.
Can I just say a number?
Yeah,
Is it 70?
it is.
Oh my gosh, actually?
Yeah, how'd you get 70?
Oh, well, I did 250.
Yep, so do you guys see why this is 250? Because it all has to add up to 360. So if this is 110, the rest is 250. So then the measure of angle D is what?
70.
So 250 minus 110 divided by 2. So 250 minus 110 is 140. Divided by 2 is 70 degrees. Very good. Is that what you got? Okay, does that make sense? So this one is cool because they don't give you the two arcs, but you, by process of elimination, we can figure out that the rest of the circle has to be 250. So 250 minus 110 divided by 2 is your answer. All right, good, good. Okay, so there's other ones too. We don't have to keep doing that. Yeah, that's it for 79. You guys good? 79? All right, let's do 80. Those of you who didn't get it, does this make sense? So basically what probably stumps you up is this, like, how do you figure that out? Well, it all has to add up to 360, kind of like a triangle that has to add up to 180 type of thing. So, all right, that's 79. Let's move on to 80. All right, lesson 80 is finding surface area and volumes of spheres. Okay, SA and volume of spheres. Now this is a weird one. This is hard to explain how we get this formula. Does anyone, for a free problem set, can anyone tell me how to find the volume of a sphere?
Do you cut it in half?
To explain it, you could, but how do you find the volume of a sphere? It's kind of abstract. It's weird. Volume.
I remember it has like 360 in it, doesn't it?
No.
No.
And surface. Anyone know surface area for a free problem set? Okay, that's all right. Volume is 4/3 pi r cubed. Surface area is 4 pi r squared. Okay, this is a tough one to remember. Where the heck did they get 4/3? Well, I'm going to explain it because it's interesting. So look at a sphere. Here's a sphere. Right? So let's cut it in half just because we can. So this is R, right? And that would mean this is R. So that's kind of cool. So you got like this, if you cut it in half, you got this little dome here, right? And so it almost looks like a cone, right? It almost looks like a cone, but a cone would go up to here. So how do you find the volume of a cone? Well, that is 1/3 pi r squared times h, right? So the volume of a cone, like this, same circle or whatever, this is volume equals 1/3 pi r squared h. Now, this looks like, this is a lot more chubby. Actually, it's twice as chubby as the cone. So this is 2/3 pi r squared h. Okay, so a hemisphere, to find the volume of a hemisphere, it's not 1/3 pi r squared h, it's 2/3 pi r squared h. But what's h? What's h?
It's the radius.
Yeah, it's the radius. So this is r squared r. What's r squared r? R cubed. So volume equals 2/3 pi r cubed. Right? So if half of a sphere is 2/3 pi r cubed, the whole sphere is 4/3 pi r cubed. So that kind of explains, this is a little, well, how do you know this is twice as much as a cone? You know, I mean, but it at least kind of gives you an idea of how they get this. So if you forget this formula for a volume of a sphere, cut it in half and try to figure it out. Okay? This is the only stretch, the 2/3 versus 1/3, but it kind of makes sense, but it's hard for me to prove it to you. Now, surface area, I have no idea why this is the case, but the surface area is equivalent to the area of 4 circles. So I mean, I'm trying, in my brain, I try to like take a piece of paper and wrap the sphere in this is called the great circle. The biggest circle in a sphere is called the great circle. So that if I take a piece of paper that's that circle and try to wrap, I can't justify why that's 4 of those pieces of paper that will cover it. I don't know why, but it's not a bad formula to memorize, right? Pi r squared is just the area of a circle. It's just 4 of them, 4 pi r squared. That's the surface area. So now, you guys can use these formulas. And most of the time when you take a standardized test, it will give you these formulas. And so I don't feel too bad about letting you use these on a test. But these are the formulas for volume and surface area of a sphere. Okay? So the other thing that this part here, this is the other thing that you need to know. That's called the great circle. So the biggest circle in a sphere, the biggest circle in a sphere. So it's right in the middle, right? Now that great circle, you can draw it anywhere. Like if you could cut it right there and there's another great circle. But the great circle, find the area of that, it's just the radius. So the radius is the biggest radius. So the way you define a sphere is interesting. How do you define a circle? Do you remember when we defined a circle? What the definition of a circle is, Janae?
Isn't it like infinite points, right?
Yeah.
It's infinite points equidistant from one another.
Yep. So on a two-dimensional surface.
Right.
So on a plane, that's what a circle is. But a sphere is the same definition. The same definition of a circle, but in space. Instead of a plane, which is a circle, it's in space. So all these points on a sphere, think about a basketball. All those points are the same distance from the center of that sphere. Okay? So a circle and a sphere have the same definition. Okay? But one is limited to a two-dimensional space. That's a plane, but one is not. Okay? All right, so that's about it.
Black math, give me some math and I'll give you some flack. Black math.